All right, so section 3.1 has to deal with higher order derivatives. We've already been finding first derivative and second derivative and translating what they mean in terms of minimums and maximums, points of inflection. Today we're going to look at what they mean in terms of position, velocity, and acceleration. It's probably one of the bigger applications that we have. If you've done physics, you've already encountered this, and now you have this extra tool to help you determine what the acceleration and velocity functions are. So we have a very straightforward polynomial function here, 3x cubed plus 7x plus 3. First derivative becomes 6x squared plus 7, and then our second derivative would be 12x. So s of t is what's used for the position function, which is going to have a unit like meters, centimeters, kilometers. The velocity function, which is the first derivative, but you'll often see it change to v of t automatically, which implies it's the first derivative. That's generally meters per second or kilometers per hour, depending on the units that you're starting with. Finally, the second derivative, which is the derivative of the velocity, is representing the acceleration function. So we'll end up with meters per second squared. So you're already familiar with all these units. Now we're just generating where they're coming from. So here's a common question that you've been answering since grade 10. A ball is thrown upwards and its height is represented by negative 5t squared plus 25t. In A, it's asking you to calculate the ball's initial velocity. Anytime they're talking about initial velocity, they want to know when t equals 0. So nothing crazy going on here. We're simply going to substitute in t equals 0, not into the original equation, but into the derivative, because it's saying velocity. So we need h prime of t. So that's going to be negative 10t plus 25. So h prime of 0 is going to be negative 10 multiplied by 0 plus 25, which equals 25 meters per second. Don't forget your units here. Part B, it's saying calculate the maximum height of the ball. So maximum height of the ball. In grade 10 and grade 11, that would be your cue to figure out what the vertex is. We're not going to do that in calculus. In calculus, we know that the maximum or minimum value occurs when the derivative is equal to 0. So we already found what the derivative is. So we have 0 equals negative 10t plus 25. So t is going to equal 2.5 seconds. Okay, so that means the maximum height of the ball occurs at t equals 2.5 seconds, but we haven't actually answered the question because we want to know the actual height. So you need to find where the y value of your vertex is essentially by substituting it into the original. So we have negative 5 times 2.5 squared plus 25 times 2.5. So when we work that out, you end up with negative 5 times 6.25 plus 2.5 times 25. Which is 37.5. So we end up with, oh no, that's not right. It's not 37.5. 62.5. And then here we're going to have negative 31.25 plus 62.5. So that equals 31.25. Therefore, the max height is 31.25 meters. In C, it wants to know when the ball hits the ground and what is the impact velocity. Okay, so when does it hit the ground? Balls hit the ground when the height is 0. So you're being asked to figure out the zeros of the original function. So we have 0 equals negative 5t squared plus 25t. So when I factor this, I'm going to be left with So therefore, the ball is on the ground at t equals 0, which makes sense. And t equals 5. So it hits the ball at 5 seconds. Then we need to find h prime of 5 because we want to know the impact velocity. So we'll have negative 10 multiplied by 5 plus 25, which equals negative 25 meters per second. So therefore, the ball hits the ground after 5 seconds with a velocity of negative 25 meters per second. Why negative? Because the ball was coming down. So the negative and the positive when we're talking about velocity is giving us the direction. So this is a typical question, and it's all about the language, knowing that maximums and minimums occur when the first derivative is equal to 0. When do you sub it into the derivative? When do you sub it into the original equation? So it's all about understanding what the question is actually asking you to find. All right, the next example. So we have the position of a particle moving along a straight line. So even though this is a cubic function, it's not moving in a cubic path per se. It's not following the same path that this graph here is indicating. What this means is you have an x-axis and there's a particle that let's say it starts at 0, it's going to go to the right, then it might turn around and come back to the left, then turn around and go back here. So it's a particle that's moving up and down on the same line, or left to right on the same line, I guess is a better way to talk about it. So here it's telling us that t is greater than or equal to 0. In the first question, it's asking you to figure out the velocity function and the acceleration function. So that's what I have right here. I have the velocity function is my first derivative, the acceleration function is the second derivative. Then it's asking you to graph the position function, the velocity function, and the acceleration function. So in order to get an accurate graph, I can use the computer and generate a very accurate graph, but I want to do the algebra along with it because on the test you're not going to have that computer to do it for you. So in order to graph properly, we want to know what the zeros are. So from here, when I factor out a t, I'm left with t squared minus 12t plus 36. So this will factor very nicely to give me t minus 6 all squared. So I have a 0 at t equals 0 and t equals 6. So that makes sense based on this graph that I originally have here. So the first equation, the starting equation, the parent equation I guess you would call it, that will tell you what your x-intercepts are. Now over here we have our first derivative. So I'm going to factor that to figure out what the zeros are for that. That will tell us where our minimums and maximums are. So if I write 0 equals, I'm going to factor out a 3. I'm left with t squared minus 8t plus 12. So 0 is going to equal 3, t minus 2, t minus 6. So I have t equals 2 and t equals 6, which I've already actually found. So I know that when I'm looking for the coordinate of this value, when t equals 6, y equals 0, so I have the coordinate 6, 0. If t is equal to 2, I know that y equals 32. And you get that by substituting into the original. So I have that coordinate 2 and 32. So that justifies this point right here. There's another value that we can figure out. So here, if I find when the second derivative is equal to 0, I find 4 is equal to t. So if I were to sub in, y will equal 4 cubed minus 12 times 4 squared plus 36 multiplied by 4. So I'll have 64 minus 12 times 16 plus 120, 144. Okay, so 64 and 144. So that's going to be 210 minus 194. right? 12 times 16. Okay, so 12 times 16. 192. Okay. So from there, we end up with 18. So that's telling us our point of inflection is at 4 and 18. And actually, I just realized I made an algebraic error here. 64 and 144 is not 210. It's 208, which makes this 16, which definitely makes more sense when I look at that graph. So we have our sketch. So now when I want to generate this graph right here for our first derivative, oops, I clicked on the wrong thing. We get a parabola, which makes sense. And then the final equation that we would have would end up being a line if we were to graph that. So I have to do that one by hand. It doesn't do it nicely on this graph right here. So when t is 0, you're all the way down to negative 24. So the first point when t is 4, we're going to have a value here. Okay, when t is 4, y is 0. When t is 5, we're at 6. So then I can draw this line. All right. So we have all of our derivatives. Now, the next question. Determine the distance traveled in the first 5 seconds. So that's why this one here is a bit trickier. A lot of students, they want to just take the 5, substitute it into the position function, and say that that's the answer. But that is only where the actual coordinate is at 5 seconds. It doesn't tell you how much it's actually traveled. So looking at the graph, there's a key point. So you follow the path that it's taking. So if the point starts at 0, so if I were to draw like a number line, for this first 5 seconds. So it went from 0 to 2. So it's increasing from 0 to 2. So it went from 0 to 2. At 2, it turns around and comes back. And when it's going backwards, we want to go all the way back for the 5 seconds. So if you want to show that on your curve, you're going in the negative direction for 5 seconds. So for the 5 seconds, you're going this way. Okay? So even though the distance you're traveling is going to be a positive value, you've gone a total of 0 to 2, however long that distance is, and then from 2 to 5. So mathematically, how do we figure that out? So the position function after 2 seconds is going to equal 32 meters. So far you've gone 32 meters. Then you turn around. So then I need to find what S of 5 is. So looking at the original function, if I substitute that in, I can tell from my graph that it looks like it's around maybe 6 meters, maybe a little less. We're going to figure that out. So I have 5 cubed minus 12 times 5 squared plus 36 times 5. So I have 125 plus 180 minus 12 times 25. So that's 125 minus 300 plus 180. So we end up with 5 when we work that out. 125, 180 is 305 minus 5. So therefore, the total distance equals 32 meters from 0 to 2 seconds plus another 5 meters to give us a total of 37 meters. You'll notice it's distance, not displacement. So even though you're going in the opposite direction, it doesn't cancel out. All right, so I'm going to stop there. There's a table that I want to fill in, but I want to do that together as a class, analyzing what all this different motion tells us about acceleration and the direction it's moving in and how you can describe the particle, but we'll do that when I come back.